Assalamu alaikum rahmatullah. I hope those are watching these videos having good health and doing great. Welcome to Fahad's tutorial, and this is the fourth tutorial of the chapter Effects of Heat on Matter. And this class is about the expansions of solid, because actually the thermal expansion of matters I need to divide it into three different parts, because I need to explain it in other video what is the thermal expansion in liquid and the thermal expansion in gas. But in this tutorial, particularly I will explain about the expansion of solid. So in solid there are three types of expansion. First is linear expansion, and then is superficial or area expansion, and third is volume expansion. So as we have three type of expansion, that in case of solid we can say that it's linear expansion, area or superficial expansion, and volume expansion. I'm coming up with more detail. Before, we need to know that it's linear expansion, and number two is superficial, or we can say it's surface expansion. So superficial expansion, and number three is volume expansion. Because solid substance, solid material will have three dimensions, like in case of length, in case of area, and in case of volume. So a solid material can expand in three aspects. So now think about the first one. What is the linear expansion? Suppose this is a rod which is actually kept it in 0 degrees Celsius. Think about, this is the rod and it's actually kept it in 0 degrees Celsius or 0 degrees Celsius, and the length from here to here, let it L0. That means the length in 0 degrees Celsius. And right now, if I say that I increase this temperature till 100 degrees Celsius, then what will happen? Then it will definitely expand. I'm just making it more larger to make it more visible. Suppose expansion is only happening in one dimensional, I mean in case of length. Though when you give heat, it will expand in all aspects, but thinking about only the linear expansion. So now you can see that from this to this is the increment in case of length. So it would be actually, if I say that this is L1, or this is L0, L1, or you can say this is L1, L2, whatever. But the concept is, this amount of expansion is known as del L. Okay, and the temperature, suppose there is 100 degrees Celsius. So now what is the concept? That amount of increment happens in case of length due to the heating, and this del L is actually depend on the previous length times the amount of temperature was changed. The amount of temperature that we are saying right now, del theta, or even you can say del T, whatever. But the thing is, the change of del theta is actually, if it is theta 1 and if it is theta 2, that means the previous temperature and the next temperature. So del theta is actually the theta 2 minus theta 1. So this is 100 degrees Celsius or 100 Kelvin. As because the change of Celsius is equivalent to the change of Kelvin. So this is proportional. Now we know that we have to make the constant of proportionality, that in case of linear expansion this is alpha. Though this is alpha, it means the relationship, but this alpha is the constant of proportionality, and this is known as coefficient of linear expansion. This is very important. So in case of alpha, this is the constant of proportionality, and it's known as, alpha is known as coefficient coefficient of linear expansion. Coefficient of linear expansion. So this is alpha. So we can say del L equals alpha L naught del theta. Now if I want to define what is alpha is equal, then we can say that alpha is equal del L divided by L naught del theta. This is the equation of alpha. So this alpha is the coefficient of linear expansion. And what does it mean actually? It means that if this L naught is 1 meter, okay, and this del theta, that means the change of temperature is only 1 Kelvin, then the amount of change in length is the coefficient of linear expansion of that materials. That means if any substance or rod is 1 meter long and I just change the temperature in 1 Kelvin, so that the amount of length that is increased is the coefficient of linear expansion of that metal or that substance. I hope you understand. You know that how I get it, this alpha is del L by L naught del theta from this. It's because this del L, that change of length, depends on the previous length and the temperature change, because we know that the temperature will increase more, the change of length will more. So the del L is definitely depending on these two things, is the multiplication process. So alpha is equal to del L divided by L naught del theta, like this. And now if I say that the coefficient of linear expansion of iron, the coefficient of linear expansion of iron is 11.6 times 10 to the power minus 6. Now think about the unit of alpha. As we say that alpha equals del L by L naught del theta, del L means length. So it means if it is length, the unit should be meter. So as it is meter, and this is also length, so this should be meter also. But in case del theta is the unit, in case of temperature the unit is Kelvin, so we can say we can erase meter from both sides. So the unit of linear expansion coefficient is per Kelvin. Right now if I say that the coefficient of linear expansion of iron is 11.6 times 10 to the power minus 6 per Kelvin, it means if a rod made of iron is 1 meter long, and if I change or increase the temperature in 1 Kelvin, then it will increase that meter. So if 1 meter length of iron is increased to 1 Kelvin of temperature, then 11.6 times 10 to the power minus 6 meter length will increase, and this is alpha. This is alpha. Okay, so alpha denotes as a coefficient of linear expansion, and this is totally different in different metals. So the coefficient of linear expansion in case of iron, copper, steel and other metals are different, as because it's a fixed value, it's the constant of proportionality. So I hope you understand the primary basic of linear expansion. Think about the superficial expansion or the area expansion. So if things can actually increase in length, so what about the area or the superficial change? Think about a box. Think about a box. So this is a box and we have length and breadth, and if a heat is given, then it will increase in case of area, in both cases. So that increase in case of area, so how we will say that this is area? So the differences of area, that means the previous area was A1 and the new area after application of heat is getting A2, So the differences of area is A2 minus A1. So that is depending on the previous expansion times the change of temperature, like this. So now this is very easy. It was previously del L, now this is area. It was previously L0, or you can say L1. Right now it's A1, or if you say this is A0, things are okay. It means the previous area. And now what is the constant of proportionality in case of area expansion? That is beta. So we can say that del A is equal beta A0 del theta. And now the equation of beta seems like previous one, del A divided by A0 del theta, or you can say A1, or if you express this temperature as T, you can say this is del T, whatever. I mean, if you understand the concept, equation doesn't fact, so del B, it can be del A by A1 del T also. So what is the definition of coefficient of area expansion? As we know that alpha is a coefficient of linear expansion in case of length, and beta is about area expansion in case of area. So we can say that unit similar. How? Because we know that A is area, so it would be meter square. Similarly, this is also area, so it will be meter square times T as a Kelvin, so meter square will be vanished and Kelvin would be K inverse 1. So the unit of coefficient in linear expansion, in area expansion and in volume expansion, in both all cases, the unit of expansion coefficient is per Kelvin. So you understand this one? Like before, if I say the beta of steel, I mean the coefficient of area expansion of steel is 22 times 10 to the power minus 6 per Kelvin. What is the meaning of it? The meaning of it is that if a steel area is 1 meter square, and the application or the change of temperature is 1 Kelvin, then the area expansion of steel is 22 times 10 to the power minus 6 meter square. So as del A, I mean, we say that this beta is equal to what? So beta is equal to del A by A1 del theta. You say that this A1 is 1 meter square in case of steel, and you also say that this is 1 Kelvin. Now you think this del A is actually 22 times 10 to the power minus 6 meter square in case of steel. So I'm just giving you the example, and as a primary level basic. So the beta or the coefficient of area expansion of steel is 22 times 10 to the power minus 6 per Kelvin. It means that 1 meter square area of a steel, and if we increase temperature in 1 Kelvin, so the expansion of its area would be 22 times 10 to the power minus 6 meter square. Okay? Just if you think about the same thing, then this is same in case of volume expansion also. In case of volume, we need to think three-dimensional. In case of volume, we need to think three-dimensional of something like that. Think about a volume. So if it is something a cubic shape, and if we see that the three-dimensional view, I mean length, breadth and height, so we can say that in all aspect it will increase, and it's a volume expansion. So similarly, like before, if the volume of the cube previous is V1, and after changing the temperature of del theta, and the new volume, the expanded volume is V2, then what will be the relation? That del V is dependent on the previous volume times the change of temperature. And then we'll find the constant of proportionality in case of volume expansion, that is del V is equal gamma V1 del theta. And now you find the del theta, gamma, that is del V divided by V1 del theta. And similarly, the unit of delta is equal to per Kelvin. Like this is actually meter cube, this is meter cube times Kelvin. So we can say that meter cube is vanished from both sides. So per Kelvin is the unit of gamma, which is the coefficient of volume expansion. Now if I say that the volume expansion of glass, the volume expansion of glass is 27 times 10 to the power minus 6 per Kelvin, then your answer is, so del this gamma, it means that if a glass shape is 1 meter cube, and if we change 1 Kelvin temperature, increase 1 Kelvin temperature, then the volume will be expanded as 27 times 10 to the power minus 6 meter cube. And this is the definition of the coefficient of volume expansion. Okay? I think I took some long time make you understand, but I hope you definitely understand if you just read it. I'm just explaining from the books so that things will be easier for you to understand, listen and watching this video, so that the next time when you'll see some sort of like mathematical problems, it will be much easier for you to solve it. So what is the wrap up of the tutorial? So if I say simply, okay, I'm just removing it. Okay. So if I say simply, what is the equation of alpha? What is the equation of alpha? Now you can say that linear expansion. In case of coefficient, the linear expansion is alpha. In case of superficial or area expansion, this is beta. And volume, this is gamma. Now you have the equation that alpha is equal del L, as it is length. So alpha is totally related with length. So del L divided by L1 del theta. Or even beta is equal del A divided by A1 del theta. Like beta is related with area and gamma is equal del V divided by V1 del theta. And then in both cases the unit is per Kelvin per Kelvin. Okay? One thing is very, very important. In a same substance, like in case of iron or copper or glass or whatever, the alpha, beta and gamma, they have a relation. What is the relation? If you multiply alpha by 2, then you will have the value of beta, as because we know that area is the multiplication or the cross product of length and breadth, two length. And if I multiply alpha by 3, then I will have gamma, as it is volume. Now you think, say 2 alpha is beta, 3 alpha is gamma. Now you think, in this case, if I want to make a relation in these two equations, I need to make a common quantity in these two equations. How can I do it? If I multiply by 3 with this thing, then it will have 3. So 6 alpha summan 3 beta, or you can say this is, if I multiply it by 2, then it will be 6 alpha equal 2 gamma. So now if you say 6 alpha 3 beta 6 alpha 2 gamma, it means that 6 alpha and 6 alpha, I got common quantity in both sides. So 3 beta and 2 gamma is equal. So right now I can say that 6 alpha equal 3 beta equal 2 gamma. And I hope you'd really understand the relations in between these coefficients of linear, superficial and volume expansion. And this is the equation that we need to use in case of mathematical problem solutions. Suppose in some questions length related data is given, but the question is to find out the volume expansion, the coefficient of volume expansion. Then you will try to find out the value of alpha, but the question is to find out the value of gamma. Then after, what you'll do, that using those data you will find first value of alpha, then multiplying by 3 you get gamma. Or if you got beta but you need to find out gamma, then what will be? So you need to use these equations. So on that time you know that 3 beta is 2 gamma. So beta is equal to 2 by 3 gamma. Or even gamma is equal 3 by 2 beta. So in both cases you can have instead of beta or gamma. Suppose you've got the value of gamma but you need the value of beta, then multiply by 3 by 2, that is 1.5. Or if you need the value of gamma or beta but you got the value of gamma, then do it. Okay? So hopefully I can make you understand in case of the thermal expansion of matter. So it's about the expansion of solid. So in case of solid, we studied about the linear expansion, the superficial expansion and the volume expansion. And next class I'm coming up some sort of mathematical problem solutions regarding this, because this is something very important that is common in our question paper. And in case of physics, I said always that do not skip any chapters, and of course do not skip any content of any chapter, because when you'll go to study higher physics you won't have chance to skip anything, and skipping is not a good policy. So student of English versions Cadet College and wherever you are watching this tutorial, I want that you love physics, you love your subject, so that some sort of things and joyfulness can grow up in your mind regarding your study, and that is helpful, that is supernaturally helpful. So take care, stay well, see you on the next class regarding some mathematical problem solutions with this. Bye.